Hello. So now we come to the last capsule of this third week, and that is what is called as odds and ends. So we'll discuss a few odds and ends, specifically one particular thing about matrices which didn't fit into the general scheme of things, but it's very important, and that is block matrices. Before we take that, let us take an example of computation of a determinant. So I want to compute the determinant of 1 plus a squared, a1, a2, dot, 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 a1, an, a2, a1, 1 plus a2 squared, dot, 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 etc., a2, an, and so on. The last row is an, a1, an, a2, dot, 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 1 plus an squared. Note that if a1 is 0, then what happens to the first row? The first row is simply 1, 0, 0, 0, 0, 0. And then we can expand the determinant by the first row, and we are down to computing a n-1 by n-1 matrix of the same type. So we may as well assume that a1 is non-zero. So now, just for convenience, let us call the matrix A. We want to compute the determinant of A. Just observe that this A is basically identity plus A naught. Where what is your A naught? A naught is AI AJ, the symmetric matrix AI AJ. The reason for writing this A as a sum of these two matrices, it's not strictly needed, but I just displayed it like this just to bring out the fact that this A naught, that's a matrix of rank 1. In fact, all rows are proportional to each other. And so, because the matrix A naught has rank 1, it is very natural to perform row operations. R2 prime equal to R2 minus A2 by A1 R1. R3 prime equal to R3 minus A3 by A1 R1, etc. Rn prime equal to Rn minus An by A1 R1. In other words, from the jth row, subtract off Aj by A1 times the first row. Now what will happen? I should perform that operation on I, and I should perform that operation on A naught obviously. If I perform that operation on A naught, what happens? I get this matrix, the lots of zeros below. And if I perform the matrix on I get this very nice pattern 1 0 0 0 0 0. And so all in all, this new matrix, that is, if I start out this matrix and make this row operations, this sequence of row operations, I will land up with this matrix A tilde. What is A tilde? 1 plus A1 squared, A1 A2 dot 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 A1 AN. The second row is minus A2 by A1 1 0 0 0 0 0. The third row and so on. The last row is minus AN by A1, etc. And there is Z after that there's 0, and then the last entry is 1. So you can actually do this calculation, and you can do it for yourself, and you can check that this is what we get. So now what we have done is that I'm going to pull out this A1 from second row, third row, etc. So I'm going to write this as 1 plus A1 squared, A1 A2, etc. A1 AN. I'm going to write as minus A2 minus AN, because I'm going to remove the 1 upon A1, and I'm going to put the A1 over here, A1 over here, etc. Remember that multiplying a given row by a number is equivalent to multiplying the whole determinant by that number. So A tilde is obtained from A by this sequence of row operations of a very specific kind, subtracting off from a given row a multiple of some other row. That does not change the value of the determinant. Remember? So the determinant of A tilde is going to be the same as the determinant of A. So determinant of A equals determinant of A tilde. And then I pulled out this 1 upon A1, 1 upon A2, 1 upon A1 from the second row, third row, fourth row, etc. So I write it as A1 to the power minus n minus 1. So factorizing a 1 upon A1 means I have to put a A1 here. Factorizing a 1 upon A1 means I have to put a A1 here. So that's how I get this A1s for the 2 position, 3 position, n position. So this is the determinant that I need to compute. Now I need to perform a bunch of row operations. So what do I do? I need to kill this A1 A2 term. How do I kill this A1 A2 term? Subtract from the first row A2 times the add to the, so subtract from the first row A2 times the second row. Subtract from the first row AN times the last row, and so on. So this bunch of row operations I need to perform. And what happens is I kill A1, A2, A1, A3, A1, AN, I get 0, 0, 0, 0, 0. But the 1 entry is 1 plus A1 squared plus A2 squared plus dot 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 plus AN squared, and A1's down this diagonal. And so expanding this by the first row, I get this A1 to the power n minus 1 will cancel with this A1 to the power minus n minus 1, and I'll be left with 1 plus A1 squared plus A2 squared plus dot 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 plus AN squared as the value of the determinant. So this is one calculation that we have done the long way, in fact. Later on, we shall see a way to arrive at this determinant without performing any calculations. Directly by inspection, we can get the value of this determinant after we do the chapter on eigenvalues and eigenvectors. After we do the chapter on eigenvalues and eigenvectors, we shall find a more efficient way to arrive at this same result. So that is a nice example, and this example I specifically chosen because this example appears very frequently in multivariable calculus. In multivariable calculus, when you do integration along surfaces in R3 or hypersurfaces in Rn, you will exactly encounter this determinant. And so this has some geometrical or significance in calculus. The other thing is an appendix, if you like, or a coda to this chapter on determinants, and this is called block multiplication of matrices. Very frequently, this idea of block multiplication will pop up, and you should not be taken by surprise. So you should know how to deal with how to do block multiplication of matrices. It's very easy, and let us just dispose it off in a few pages. So first of all, let us consider the simplest block matrices, a 2n cross 2n matrix. What is a 2n cross 2n matrix? I can think of a 2n cross 2n matrix as being made up of 4 n cross n matrices. So I take 4 n cross n matrices A, B, C, D. Each of them is an n cross n matrix. So if I put A, B, C, D as a 2 by 2 block, then I get a 2n cross 2n matrix. So this writing a 2n cross 2n matrix in this form A, B, C, D is called partitioning the matrix. Partitioning the matrix. So now, how to multiply a pair of 2n cross 2n matrices? So I've given 2 such matrices. So I'm going to partition each of them. So I'm going to do a partitioning. I'm going to have the first matrix M as A, B, C, D, and the second matrix N as P, Q, R, S, where A, B, C, D, P, Q, R, S are all n cross n matrices. So what is the product? The product is basically the block A, B, C, D multiplied with P, Q, R, S. Suppose I do the multiplication. Suppose I blindly do the multiplication. I simply get AP plus BR, AQ plus BS, CP plus DR, CQ plus DS. Now you will object. You will say that A, B, C, D are not real numbers. So this kind of multiplication needs justification. In other words, I just do a formal multiplication of 2 by 2 matrices, and I get star, and I claim that AP plus BR. What is AP plus BR? That's an n cross n matrix. AQ plus BS is an n cross n matrix, and so on. So this particular thing that you get is a 2n cross 2n matrix. And this 2n cross 2n matrix is exactly going to be the product of M and N. The product of M and N that we were trying to compute. Now this will need a justification. So how do I justify this? So exercise, prove this equation, prove this rule for block multiplication. So just to get you started on this exercise, let us check. So now, how do I have to prove? First, let us do a simple exercise. Let us consider a column vector in R2n. Column vector with 2n entries. x1, x2, xn, y1, y2, yn. There are 2n entries. The first n entries, I'm going to abbreviate it as x. And the last n entries, I'm going to abbreviate it as y. In other words, this is also a partition matrix. This is also kind of a partitioning of a 2n cross 1 matrix into in two components. The first entry is a n cross 1 matrix. The second entry is also an n cross 1 matrix. So we have partitioned this 2n cross 1 matrix into two n cross 1 matrices. So first, let us see how to multiply A, B, C, D with a partition V, with another partition matrix X, Y. Right? V remember is X and Y. This column X, Y. So again, a formal manipulation will be AX plus. So put the X and put the Y, and it will be AX plus BY, CX plus DY. First, let us verify this simpler identity. Okay, AX plus BY is an n cross 1 matrix, CX plus DY is again an n cross 1 matrix, and so as far as sizes of the matrix are concerned, everything is working out. Let us verify double star. Directly do the verification. A is an n cross n matrix. Write it incompletely. A11, A12, da da da, A1n, da da da, AN1, AN2, da da da, ANN. Similarly, write B, B11, B12, B1n, etc. Bn1, Bn2, Bnn. Write C, C11, C12, C1n, etc. Cn1, Cn2, Cnn, and likewise for D. And then you put this x1, x2, xn, y1, y2, yn. Just completely do the matrix multiplication the usual way. Very first lecture. How did you do the matrix multiplication? Do that and see what you get. You're going to get exactly this double star. So this equation double star has been verified. Now we want to check this condition. Now we want to check that if I multiply these two blocks A, B, C, D with the block matrix P, Q, R, S, I get this block matrix AP plus BR, AQ plus BS, CP plus DR, CQ plus DR. Now how do I verify the identity of two matrices? How do I check that two matrices are identical? One way to do it is prove that the first columns are the same, prove that the second columns are the same, and so on. So let us check it column wise. Let us verify the identity column wise. Having established double star, we now check the correctness of this equation. So check it column wise. Check that the column wise they're equal. The first column on the left hand side should be the same as the first column on the right hand side. What is the first column of a matrix? First column of a matrix, remember, you obtain by multiplying the matrix to 1, 0, 0, 0, 0, 0. So you compute A, B, C, D, P, Q, R, S, and you apply it to the 2n cross 1 matrix, 1 followed by zeros. Okay, so what do you get? We already checked how to multiply a block matrix with a column vector. We already done that. Just now we have done that. So it will basically be, now I'm going to call the first n entries of this as E1 cap 0. So P times E1 cap plus Q times 0. So that is P times E1 cap. R times E1 cap plus S times 0. So R times E1 cap. So I had done the multiplication of PQRS with this 2n cross 1. We got this. What is P E1 cap? P E1 cap is exactly the first column of P, and R E1 cap is the first column of R. So again, this is a column. This is like an X and this is like a Y in the previous. So again, it will be AX plus BY kind of a business. So AP E1 cap plus BR E1 cap, CP E1 cap plus DR E1 cap. Because you have checked the rule for block matrices, where you got a 2 by 2 where you got a 2 by 2 block consisting of n cross n matrices, and you got a 2 by 1 block consisting of n cross 1 matrix. That we have checked, that double star. We have checked double star. So we got this. So what is this? This is going to be the first column of AP plus BR of E1 cap. AP plus BR of E1 cap is nothing but the first column of AP plus BR. CP plus DR of E1 cap is the first column of CP plus DR. So we have checked that the first column on the left hand side is the same as the first column on the right hand side. Do the same kind of mathematics with all the columns. Similarly, check that the jth column of both sides of star agree, and thereby you would have checked the correctness of this block matrix multiplication. Please carry out this exercise by yourself. Convince yourself how to multiply matrices which are given in block, or which are partitioned. Let us look at a simple example of this block multiplication of matrices. So I'm going to take a lambda is a 3 cross 3 matrix. Lambda is a 3 cross 3 matrix. I have taken a 3 cross 3 skew symmetric matrix, but the skew symmetry will come up later on. It's not going to come up in this page. So I want the exercise is compute the determinant of the 2n cross 2 or the 6 by 6 matrix. This is a 6 by 6 matrix. I minus lambda I. Written the 6 by 6 matrix has been written as in block form. 4 blocks of 3 by 3 matrices. 4 blocks of 3 by 3 matrices. Block the partitioned the partitioning of a 6 by 6 matrix into 4 3 by 3 matrices, which are the I minus lambda I. So that's my matrix. That's my matrix A. Now, if I want to, if this instead of I, if you had 1 1, and if you had a scalar lambda minus lambda and a scalar lambda, then how do you calculate the determinant? The way you calculate the determinant will be to make this 1 2 entry as 0, right? In other words, you would like to add to the second row. I think I should be minus lambda times the first row. I think I made a mistake. You will add to the first row. Add to the first row lambda times the second row. Or you could also do the same thing. You could also add to the second row minus lambda times the first row. That should also be fine. That should also be. I mean, okay. Either you have two options. Either make this instead of this, make this minus lambda kill this 1 2 entry, or kill the 2n entry. Either of the two options are okay. So here I'm suggesting that you add to the second row minus lambda times the first row. So that means that will kill the 2n entry. Now, what is the logic behind doing a row operation? Remember, performing a row operation on a matrix is equivalent to pre-multiplying the matrix by the corresponding elementary matrix. So what is the corresponding elementary matrix? I should obtain it from II. So add to the second row minus lambda times the first row. The corresponding elementary matrix is E. Now you will object. You will say that this is not really an elementary row operation, because these rows are not really rows of, they are not rows really. They are actually blocks. They are actually, it's not really a single row. I'm taking a bunch of n rows. The second row here is really not one single row. It's a bunch of n rows. So what do you mean? What do you mean by saying that performing this row operation is equivalent to pre-multiplying the matrix by the corresponding elementary matrix? Let us verify this rule directly. Let us multiply E and A. So what is EA? I 0 minus lambda I. And what is A? I minus lambda I. Let us apply the rule for block multiplication. The rule for block multiplication is you're going to get I times I plus 0 times lambda. That will be the first entry. Second entry will be minus lambda plus 0. That's how you see a minus lambda there. The 2 1 entry will be the block in the 2 1 position will be minus lambda I plus I lambda, that is 0. And the 2 2 block will be lambda squared plus I. Okay, but that is exactly what you're going to get. So that is exactly what you're going to get if you do the row operation directly. If you add to the second row minus lambda times the first row, you're going to kill the 2 1 entry, and you're going to get I plus lambda squared. So instead of so what I said is that the basic rule, adding to a given row a multiple of the first row, formally carries over even for block multiplication, even for block matrices. The formal rule is correct. That's what we have checked. We have checked that we have actually done the multiplication of E and A, and we've gotten the desired result. But now, what is the determinant of E? The determinant of E is 1, right? So A can be determinant of A is the same as determinant of EA with the product theorem, but determinant of EA is the same. But what is EA? EA is this matrix I minus lambda 0 I plus lambda squared. But so this is what is this? What is this determinant? The value of this determinant is determinant of I plus lambda squared. Now, how do I go from this step to this step? How do I go from this step to this step? That I'd like you to prove that yourself. The justification from here to that. More generally, when you have a partition matrix I P 0 Q. When you have a block matrix I P 0 Q, and I want to calculate the determinant, I'm going to get the determinant of Q. All are n cross n blocks. You first expand by the first row. You'll get the smaller matrix. Keep expanding by the first row n times. After n iterations, you'll get this equation. So this is generally true. So in particular, the determinant I minus lambda 0 I plus lambda squared is basically determinant of I plus lambda squared. Now, how do I further simplify this determinant of I plus lambda squared? That we shall see later. We have to further to carry out the calculation further, to further simplify this. We'll have to rely on the theory of eigenvalues and eigenvectors. Okay, that we will postpone. Another example of block multiplication. I'm going to take the block matrix J. J is the block matrix 0 minus in 0. A is a matrix of what size? A is a matrix of size 2n by 2n. J is a matrix of size 2n by 2n. Okay. So now I'm going to choose a matrix A such that A transpose JA equal to J. So A is a matrix such that A transpose JA equal to J. Exercise, show that determinant of A is either +1 or -1. How to do that? It is very easy. A transpose JA equal to J means determinant of A transpose JA equal to determinant of J. Use the product theorem. Determinant of A transpose into determinant of J into determinant of A. Determinant of J is non-zero. J is a non-singular matrix, so determinant of J cancels on both sides. Determinant of A transpose is the same as determinant of A. So determinant of A, the whole square is 1. So determinant of A is either +1 or it's -1. In fact, determinant of A has to be 1. It can't be -1. You can rule out, you can eliminate the possibility determinant of A is -1. But that elimination of that possibility is not completely obvious. It requires some work, and we can't do it at this stage. You can, but a lot of wrestling. There's one way to do it is to do a lot of wrestling and get the result. And the other way to do it is to do it cleverly using eigenvalues and eigenvectors. So we are not going to do the wrestling match. We are going to do it cleverly, but later if time permits. However, if n equal to 1, then J is a 2 cross 2 matrix. 0, -1, 1, 0. And A is a 2 cross 2 matrix, A, B, C, D. Then this equation reads, take the transpose of A, B, C, D, multiply by J, write down A, B, C, D, and you write J again. Do the matrix multiplication and see what you get. You can actually check that AD minus BC is 1. So for the n equal to 1 case, you can directly verify this, that the determinant of A must be 1 and not -1. So the case when n equal to 1, you can check by yourself. Okay. Now next question is an exercise for you. We had talked about multiplication of block matrices, 2n cross 2n block matrices. What about rectangular matrices? Suppose I got a rectangular matrix of size n plus m cross k plus l. And I do this partitioning. A is a n cross k block. B is a n cross l block, etc. C is a m cross k block and D is a m cross l block. What should be the block sizes of P, Q, R, S? How would you specify the sizes of the block P, Q, R, S? such that the block multiplication is possible. So that what I want, AP plus BR, AQ plus BS, CP plus DR, and CQ plus DS. Do you think that this product of these two border partition matrices will be exactly this partition matrix? How should I specify the sizes of P and Q, P, Q, RS? Please think about this. And second, is this equation correct? True or false? Is this equation a correct equation? Is this block multiplication rule correct? Please verify, do the verification. Okay. Finally, let us, now that I introduce this business of the J matrix, let's play some games with J matrix. Now let G be the set of all matrices 2n cross 2n matrices A, such that A transpose JA equal to J. That is, pick all those matrices A with the property A transpose JA equal to A. Does the identity matrix satisfy this? Does A equal to identity qualify? Yes, it does qualify. So surely the identity matrix is in G. Is J in G? Yes, it is. Is it true that if A transpose JA equal to J and B transpose JB equal to J, then is it true that AB transpose JAB equal to J? Please check. Answer is yes. So if A and B are in G, then AB is also in G. Also, if A is a matrix which satisfies A transpose JA equal to J, then A inverse will also satisfy the condition A inverse transpose JA inverse equal to J. In other words, if A is in G, then A inverse is also in G. Okay. Remember that if A is a matrix with this property that A transpose JA equal to J, then the determinant of A is plus minus 1. In fact, it's going to be plus 1, but that's a different story. And so such a matrix is invertible. So A inverse makes sense. Okay. So this is a very curious property of the set of matrices G. Whenever the identity matrix is in G, whenever two matrices are in G, the product is also in G. And whenever a matrix is in G, its inverse is also in G. So suppose I've got a set of matrices. Suppose I've got a set of n cross n matrices such that the identity matrix is in the set. If you pick two elements A and B, if I take two matrices A and B in the set, the product is in the set. If A is in the set, then A inverse is also in the set. Then such a set is called a group of matrices. So what we have proved is that G, the set of all matrices satisfying this equation A transpose JA equal to J, forms a group, is a group of matrices. This group has a certain name. It is called the symplectic group. And this symplectic group is one of the most important groups that plays a very, very crucial role in modern physics. I think we'll stop this here. And with this, the material for the third week